Okay, why decreasing wavelength? Because the radio wave has got a maximum wavelength, whereas the gamma rays has got the least wavelength. So here they might ask you like what is the phase angle between current and voltage if the circuit is purely resistive. Hi guys, welcome back to my physics class. Okay, so in our previous video we had done some preparation for our second quarterly exam. So as you know, like we have 4 chapters. Today let us work on MCQs. Okay, as I observed, like most of the students find difficulty in MCQs. So I've taken some of the synopsis, like some of the most important, most expected topics from all the 4 chapters. As you all know, we have alternating current, electromagnetic waves, ray optics, and wave optics. So from these chapters, I've taken some of the synopsis. The topics. I think it might help you. So let's watch it. Okay. Yeah. So as we know, I mean, in my previous video, I had already taught this. Okay, in case if you want in detail, you can just check my previous video. So here they might ask you like, what is the phase angle between current and voltage if the circuit is purely resistive? Okay, so as you know that if it is purely resistive, then yeah, what might be the phase angle? The phase angle is denoted by phi. So phi equals 0 degree, because voltage and current, they both are in phase, so there's no angle, right? So that's the reason the phi is, the phase angle is 0 degree. But in case if it's purely inductive circuit, okay, just recall, in pure inductive, if it's a circuit is purely inductive, then current was lagging the voltage. So how much times it was lagging? Around 90 times, right? I mean, current was lagging the voltage, where voltage was leading the current for purely inductive circuit. So again, the phase angle will be 90 degree. Okay, so 90 degree times it was varying. So for pure capacitive circuit, again here the current was leading the voltage by 90 degree. Okay, so that's the reason again here the phase angle is 90 degree. And then we have something called as resonance. Okay, so I hope you know the meaning of resonance over here. Resonance is basically a pure resistive circuit itself, because here the inductive reactance and capacitive reactance will be equal, right? So again, if it's purely resistive circuit, again the phase angle will be 0 degree. Okay, so please remember these points which might help for MCQs. Okay, so moving to the next, yeah, we have something called as transformer in this chapter. So please know what is transformer. Okay, on what principle this transformer works. So as we know that the principle, the transformer works as mutual induction, and we have 2 types of transformers: step up transformer and step down transformer. Okay, the name itself tells. So step up transformer. Okay, I have referred one drawing over here. You can see there are 2 coils over here. Okay, so in this case, the primary coil. Um, Okay, so you can see here the number of turns in the primary coil. Okay, number of turns in the primary coil is less than number of turns in the secondary coil. Okay, so that's the reason this is step up transformer. Okay, what is step up transformer? Where number of turns, step up, the number of turns in the secondary coil is more than the primary coil. Okay, but if it is step down transformer, the number of turns in primary coil will be more than secondary coil. Okay, so that's the difference which you should be knowing. Okay, so remember, if it is step up transformer, okay, so if it is step up transformer, then number of coils in the secondary will be greater than number of coils in the primary. But if it is step down transformer, the number of coils in the primary will be greater than number of coils in the secondary. Okay, so please remember this point, it might help you again. Okay, and we have all the types of energy loss. This can be asked for 2 marks also, but in terms of MCQs, if they ask you, like we know that there are laws, like 4 losses: loss due to heating, loss due to flux leakage, loss due to eddy currents, and loss due to hysteresis. Okay, so why there is a loss due to heating, or this loss due to heating is also called as copper loss. Okay, so why this loss occurs means because of a, the windings, because of their resistance. Okay, because of their low resistance, or the thick wires are used. Okay, so that's the reason what happens, there might be a loss due to heating, or also called as copper loss. Okay, and then loss due to flux leakage. Okay, it's like using laminated sheets or windings of primary and secondary coil. So these are some of the causes for the loss due to flux leakage. Okay, and then you have something called as loss due to eddy currents. Okay, yeah, again here we are using a thin laminated core or soft iron cores are used. So this will cause what? Eddy currents, the loss due to eddy currents. And then finally you have loss due to hysteresis. Okay, so this is due to repeated magnetization and demagnetization that causes what? The loss due to hysteresis. Okay, so these are the four energy losses what you have to know in the transformer. Okay, and this is one of the most important question, that's condition for resonance in LCR circuit. Okay, the questions can be asked in many different ways. Okay, if it is a resonance, okay, if resonance occurs, for example, the radio tuning is a very good example for resonance. So these are the conditions what you should be knowing. So if there is a resonance, then inductive reactance and capacitive reactance will be equal. Okay, so inductive reactance is given by what? XL is given by L times omega, where L is inductance and omega is angular frequency, and XC is given by 1 by C omega. In case if they both are equal, that is L omega equals 1 by C omega, what happens? You get omega square equals 1 by LC, where omega is what? Angular frequency. Angular frequency is what? 2 pi times the frequency. So omega can be taken as, if I'll just take this root on both the sides, so I get omega as 1 by root LC, and then omega can be taken as 2 pi times F equals 1 by root LC. So in case if they ask you what's the resonant frequency, then you have a formula, F equals 1 by, this 2 pi comes over here, 2 pi times root of LC. Okay, so this is a resonant frequency. Okay, so this is a condition for resonance. Please remember, where inductive reactance will be equal to capacitive reactance. In case if they both are equal, then what happens? The impedance will be equal to resistance. I hope you know the meaning of impedance. Impedance is a resistance offered by complete LCR circuit. Okay, and R is a resistance offered by a just a resistive circuit. Why they both are equal means we have a formula, impedance formula, that is Z equals root of R square plus XL minus XC the whole square. In case if they both are equal, what happens? You get Z equals root of R square, which is nothing but equal to R. Okay, so this is one more condition for resonance. Okay, this might help you for your numerical also. Next, we have something called as power factor as unity over here. So what is this power factor? Power factor is cos 5. Okay, cos 5 will be equal to 1. Okay, so if cos 5 is 1, what is the value of 5 here? We know that 5 is cos inverse of 1. So cos inverse of 1, you can take it as 0 degree. Okay, so in my previous slide, I had mentioned what is the phase angle between a voltage and current in case if it's a pure resonance circuit. We had mentioned as 0 degree, right? Why 0 degree? Because its power factor is 1. Okay, this is the most expected multiple choice question. And then you have something called as phase angle. Yeah, the same thing, the phase angle is 0 degree. Okay, so please remember this is a most important question. It can be asked in like most of the time we expect in MCQs, or it can be like, it might help you for your numerical questions also. Okay, so now moving to the next chapter we have is electromagnetic waves. Okay, so mainly learn what is displacement current. Okay, and then you should know the formula for the displacement current. It can be asked again in the MCQ. So the displacement current is given by epsilon naught times d phi E by dt. Okay, so what is epsilon naught? It is a permittivity in aero vacuum, and d phi by dt is what? The rate of change of electric flux. Okay, why electric flux means the current, whatever the displacement current is produced due to the changing electric field. Okay, so please remember this point. Again, this is very important. Due to the change in the electric field, there is a displacement current. Okay, so this is the most expected question. And then, the expression for speed of electromagnetic wave. So please remember this formula where C equals 1 by root of mu naught times epsilon naught. In case if it is a speed of electromagnetic wave in free space, it is taken as C. In case if it is a speed in terms of material medium or something, then the same formula you write 1 by root of, but instead of mu naught you take mu, instead of epsilon naught you take just epsilon naught. Okay, this is just speed of light in, not C, it is V. Okay, because it's a speed of light in material medium, where speed of light is C. Okay, speed of light in air or vacuum is C, which we all know the value of speed of light in air or vacuum is 3 into 10 power 8 meter per second. Okay, so this is a most expected question. And then okay, so you have we have 7 electromagnetic waves, right? So we can remember using one of the mnemonic. Okay, so I use this mnemonic, That's a rabbit meat in a very unusual, expensive, I'm just writing it as expensive garden. Okay, so I'll take R. R stands for radio waves. Okay, and M stands for microwaves. And I stands for infrared rays. Okay, so V stands for visible light. Visible light, and U stands for UV rays. Okay, and X stands for X-rays, whereas G stands for gamma rays. Okay, so you should know the order. Okay, of course you will remember the 7 electromagnetic waves, but it should be written in one particular order. Okay, I have written in terms of decreasing wavelength. Okay, I have written this order in terms of decreasing wavelength. Okay, why decreasing wavelength? Because the radio wave has got a maximum wavelength, whereas the gamma rays has got the least wavelength. Okay, so then yes, of course, that's a reason, right? In our telecommunication, most of the thing we use radio waves. Why? Because it has got the maximum wavelength. Okay, and whereas gamma rays has got the least wavelength, that's the reason we write it in this order. Okay, so remember, this order is written in terms of decreasing wavelength, where we know that wavelength is inversely proportional to frequency, right? So if it is decreasing wavelength, then it is written in terms of increasing frequency. Okay, so please remember this order, and all the uses you should remember in this chapter. Okay, so that's what we can expect from this chapter, and it's a very simple chapter to score as well. Okay, next, moving to the ray optics. Of course, here many derivations are there, and most expected derivations are there. Okay, but in MCQs you should be knowing what's the relationship between focal length and radius of curvature. You have already learned in your grade 10. Okay, so radius is 2 times the focal length, or you can say focal length is half of the radius of curvature. Okay, so this formula is applicable only for mirrors. Okay, so many of them have this confusion, like is it applicable for lens or what? No, this formula is applicable only for the mirrors. Okay, it can be concave or convex mirror. Okay, so and remember, like focal length, it depends on refractive index. In case if it's a lens or something, focal length depends on refractive index as well as radius of curvature. From our lens makers formula also we have that is 1 by f equals n minus of 1 times 1 by r1 minus 1 by r2. Okay, so from that formula also easily I can say focal length depends on refractive index and radius of curvature. Okay, and you can see here focal length is inversely proportional to refractive index. Remember this point. Okay, if you remember the formula, it's easy to tell. Focal length depends on refractive index and radius of curvature, and it does not depend on object distance, image distance, and all. No. Okay, but here you can easily say focal length is inversely proportional to refractive index. More the refractive index, lesser the focal length. For example, now diamond has got maximum refractive index, so that's the reason we say the focal length of the diamond is less. Okay, so like this you can apply this. And then we have something called as critical angle. Yeah, this is a most expected question which comes in total internal reflection. So you might be knowing what is total internal reflection, where what happens as you increase the angle of incidence, okay, when light should travel from denser to rarer medium. Always, that's a one condition where light should always travel from denser to rarer medium. So what happens? It will bend away from the normal if it travels from denser to rarer. Okay, and again as you increase the angle of incidence, what happens is again it will bend away from the normal. At one particular angle of incidence, what happens? The light will graze the surface. That means the angle of refraction is 90 degree. Okay, so such angle of incidence we call it as critical angle. So please remember, critical angle is angle of incidence itself, but where the angle of refraction is 90 degree. Okay, so that's what is called as critical angle. Now, in case if angle of incidence is greater than the critical angle, then what happens? The light will completely gets reflected back. So this phenomenon is called as total internal reflection. Again, it's the most expected question. That's what are the conditions for total internal reflection? So you observed here, what is the first condition? Light should always travel from denser to rarer medium, and then as the angle of incidence should always be greater than critical angle. Only then light can reflect back. Okay, so these are the two major conditions for total internal reflection. I think the examples are mirage and on a the summer, like on a highway road, you can see there's a wet patches and all. Okay, it looks like wet patch, but as you go closer, there's no wet patch. Okay, so these are some of the examples of total internal reflection. And then you have something called as refractive index depends on speed of light. Yes, we know the formula N equals C by V. Yes, it depends on speed of light. So please remember this. And then angle of minimum deviation depends on refractive index and angle of prism. Okay, we have a formula also for this, right? That is delta equals N minus of 1 times A. So it depends on refractive index as well as it depends on angle of prism. Okay, so all these things you should be knowing, like in MCQs, these are something which can be asked. Okay, so now, for example, now, you have taken a prism where a light strikes, and what happens? There is a bending of light. So, which light bends the most? That's a violet light. Why? Because it has got a less wavelength. Okay, so remember, if it is a wavelength is less, then the bending is maximum. Whereas in violet light, what happens? The wavelength is less. So, wavelength is less, so the bending is more. But in case of red light, the wavelength is more. That's the reason the bending is least. Okay, so this is one point what you have to remember. Now, the same glass prism I'll immerse in water. Okay, so what happens to its focal length? Basically its focal length will increase. Okay, so remember this point, very important. Okay, when a glass prism is immersed in the water, what happens? The focal length increases. If a focal length increases, refractive index should decrease. Why? Because focal length is inversely proportional to refractive index. Okay, please remember this point. Then we have something from optical instruments, that is simple microscope, compound microscope, and then telescope, astronomical telescope. That's a refracting telescope. Okay, so simple microscope, always object should be placed in between pole and focus. Only then a magnified image is formed. Okay. So it should always place in between a pole and focus. That's the reason what happens, the image formed will be virtual and erect. So that's an example from a simple microscope is a magnifying glass is a very good example. And then coming to the compound microscope, again here you will be using two convex lens where a focal length of a objective should be less compared to eyepiece. So please remember this, and whatever the image formed from the objective lens will be real and inverted. Okay, and then astronomical telescope, here it's ulta, like objective lens will be of larger focal length, whereas the eyepiece is of shorter focal length. Okay, why? Because it should have a high large gathering power, right? So these are the reason why the properties of astronomical telescope, that's a large aperture. Okay, they should use a large aperture and large area of objective. Why? Because they should have a high light gathering power, because astronomical telescope is used to view the objects out of the space, right? That's the reason the objective which is near the object, that should have a highest focal length. Okay, so that's the reason, and of course it should provide a better resolution. Okay, so these are the properties of astronomical telescope. And then coming to the wave optics chapter, the last chapter, you should be knowing what is wavefront. Okay, so yeah, Huygens is the one who introduced this concept wave optics. And what is wavefront here? It's a surface of constant phase difference. Okay, and then it depends on shape of the source is. Okay, if a source is point source, okay, so what happens if a source is point source? What happens? The wavefront, whatever the produced is spherical wavefront. Okay, and in case if a source is line source, then the wavefront produced is cylindrical. And in case if the light is coming from very far, that means we take a parallel rays, right? So that time what happens? The shape of the wavefront is planar wavefront. Okay, so one example I'll give you. So for example, point source, I'll just take a point source. First draw the rays of light. Okay, so we know that light is produced in all the directions. Okay, I'm drawing the rays of light over here. Now, how to draw the wavefront means always wavefront is drawn perpendicular to ray of light. Okay, if this is a rays of light, then I'll draw perpendicular line will give me the wavefront. So when I join everything, then the wavefront what I'm getting is spherical wavefront. Okay, like this you can try for all. Like you can try if a light is traveling, passing through convex lens, how is the shape of the wavefront? All that you can just give a try. Okay, so these are some of the important topics which you should be remembering. And then you have Young's double slit experiment. Okay, in this they can ask you the fringe width formula. You don't have a derivation, you have just a formula, that's beta equals lambda capital D by small d. It's just the width. What is the width, fringe width formula? So lambda stands for wavelength of light, where it should be having a coherent source because single wavelength, and capital D stands for distance between a slit and the screen. Okay, capital D is distance between slit and the screen, and small d is what? Distance between two slits. Okay, small d is distance between two slits. Okay, so you should be knowing this formula. From this formula, there can be many questions they can ask. For example, if I increase the distance between slit and the screen, okay, in case if I increase the distance between slit and the screen, what happens to the fringe width? So use this formula. From this formula, you can say that beta is, okay, so beta is yeah, directly proportional to distance between slit and the screen. So we can say that beta is, okay, so we can say that beta is directly proportional to distance between slit and the screen. So we can say that as distance increases, fringe width also increases, because as they are directly proportional. Okay, but in case if I what to say, if I reduce the size of the slit, okay, the size distance between the two slit is small d, right? In case if I reduce the distance, okay, if I reduce the distance, what happens to the fringe width? From the formula easily we can say that they are inversely proportional. So if their distance is decreased, therefore the fringe width will increase. Okay, because they are inversely proportional. So please remember this point. Okay, also it depends on wavelength of light. Okay, now we have a red light and we have a white light. Okay, in which case beta is maximum? You just let me know through comments. Okay, so you just think how it depends on wavelength, how fringe width depends on wavelength. Fine. Okay, so moving to the next. Yeah, most important condition for constructive and destructive interference. Okay, constructive interference means what? Whenever there is an interference, there is a maximum intensity. So such intensities we call it as constructive interference, where a bright bands are formed. Okay, so these are the phase difference formula. Okay, so the phase difference is 5 equals 2n pi. Please remember phase difference. Easily you can remember path difference by using this formula. So path difference can be taken as delta x equals lambda by 2 pi times phase difference. So substitute 5 as 2n pi, cancel 2 pi, 2 pi. So you will get n times lambda. So you are getting n times lambda. So that's a path difference. So that's a relationship between path difference and phase difference. So if you remember phase difference, easily you can write the path difference. Similarly, even here. Okay, so here is also phase difference is 2n plus 1 times pi, or also you can say it as n plus 1 by 2 times 2 pi. Like how we have n 2n times pi, I mean n times 2 pi. Here we have n plus 1 by 2 times 2 pi. Also you can write this also as well as this, and then phase difference, you will get this formula. Okay, so remember this. Okay, so these are the most important topics. And finally, you have something called as Malus law, where intensity is directly proportional to square of cosine of angle between them. So remember its formula, where I equals I naught times cos square theta. Okay, so I naught is the initial intensity which is striking the polarizer. Okay, and then cos square theta. Theta is the angle between the those pass axes. Okay, the pass axis between the polarizer and the analyzer. Okay, so this is a formula, very important formula. Remember this formula. And also one hint, just remember, as the light strikes the polarizer, its initial intensity will reduce to 50 times. I mean, it will reduce by 50%. So that's the reason whatever it's entering here, we write this intensity as I naught by 2, because its intensity is reducing almost 50%. It is reducing from initial intensity. And then finally, what intensity we are getting it over here? So we will get final intensity can be taken as, we have a formula I naught cos square theta, right? So I naught should always be written as I naught by 2, because initially it is already reduced to 50%. So I naught by 2 times cos square theta. Okay, so remember, in case if an angle is given as 60 degree, apply 60 degree over here and take cos square 60. Cos 60 is 1 by 2, cos square 60 can be taken as 1 by 4. Substitute and you will get the final formula. Okay, so these type of questions can be asked in MCQs. Actually they should not ask a numerical question. Okay, so only such application questions can be asked in MCQs. Okay, yeah, so here are some MCQ questions which I've taken from this one model paper. So you can just refer this. So I'll be attaching in the. So thank you for watching. See.